Here is a sequence of numbers that grows so violently it outruns almost everything in mathematics, and then, against all reason, falls to 0. Take the number 4, apply a simple rule, which I will show you in a moment. The sequence that comes out begins quietly, 4, 26, 41, 60. Nothing alarming, but it keeps climbing and climbing. Before it is finished, this sequence reaches a number with more than 121 million digits, a quantity so large that comparing it to the number of atoms in the observable universe is meaningless. And then it comes back down. Term by term, over an unimaginable number of steps, it descends and it ends exactly at 0. This is a Goodstein sequence. What makes it one of the strangest objects in all of mathematics is not that it explodes, it is this. Every Goodstein sequence, no matter where it starts, eventually reaches 0. This has been proven, it is true, but the standard axioms of arithmetic, the rules we use to prove everything else about the whole numbers, cannot prove it. Not because we have not been clever enough, because it is impossible. In 1982, two mathematicians proved that the truth of this statement lies permanently beyond the reach of ordinary arithmetic. Last time, with the Collatz conjecture, we ended on a question: could a simple statement about numbers be true and yet unprovable? With Goodstein sequences, that is no longer a question, it is a fact. This is what that fact looks like. Everything starts with a way of writing numbers you have probably never seen. We are used to base 10. The number 234 means 2 hundreds, 3 tens, 4 ones. Computers use base 2, where every number is a sum of powers of 2. Take the number 35. In base 2, 35 is 32 plus 2 plus 1, that is 2 to the 5th power, plus 2 to the 1st, plus 1. But look at those exponents, 5 and 1. We can write them in base 2 as well. 5 is 4 plus 1, which is 2 squared plus 1, so 35 becomes 2 raised to the power of 2 squared plus 1, plus 2 plus 1. And we can keep going, writing every exponent and every exponent's exponent in base 2, until the only symbols left anywhere on the page are 2's and 1's. This is called hereditary base 2 notation. The base inherits all the way down, into the exponents and into the exponents of the exponents. Nothing remains except the number 2 stacked into a tower and a scattering of 1's. It looks like a strange thing to do to a number, but it is the engine of everything that follows. Because once a number is built entirely out of a single base, we can do something to that base. We can change it. The rule has 2 steps, and the tension between them is the whole story. Start with a number, say 3. Write it in hereditary base 2. 3 is 2 plus 1. Step 1. Bump the base. Replace every 2 with a 3. 2 plus 1 becomes 3 plus 1, which is 4. Step 2. Subtract 1. 4 minus 1 is 3. That is 1 full step. Now we repeat, but the base keeps climbing. 2 became 3, 3 becomes 4, 4 becomes 5, and on forever. Each step, we rewrite the number in the current hereditary base, bump that base up by 1, and subtract 1. Watch what happens to 3. After the first step, it is 3. Bump the base to 4, subtract 1, still 3. Bump to 5, subtract 1, now it falls to 2, then 1, then 0. The sequence for 3 is short. It barely stirs, then quietly dies. So far this seems harmless, but notice the tension built into the rule. Bumping the base can increase a number enormously. Replacing a 2 with a 3 deep inside a tower of exponents is a violent operation. Subtracting 1 chips away a single unit. It is a tug of war between an explosion and a trickle. For the number 3, the trickle wins almost immediately. For the number 4, the explosion takes over, and it does not let go for a very, very long time. Change the starting number from 3 to 4, and the sequence detonates. 4 in hereditary base 2 is 2 to the power 2. Bump the base. 3 to the power 3, which is 27. Subtract 1, 26. In a single step, we have leapt from 4 to 26. Bump the base to 4. 26 becomes 42. Minus 1 is 41. Bump to 5, 60. The subtraction is there at every step, faithfully removing 1. but the base bumping is overwhelming it. The number climbs into the hundreds, the thousands, the millions, and far beyond. How high does it go? The Goodstein sequence starting at 4 reaches a maximum value of 3 times 2 to the power 402,653,211 minus 1. That number has more than 121 million digits, and the sequence does not reach 0 until it has taken more than that same astronomical number of steps. All of this for a starting value of 4. Start at 19, and the numbers stop having any name we can relate to. The peak so far exceeds the Goodstein 4 maximum that writing one as a fraction of the other is pointless. These sequences do not merely grow large, they climb past every quantity that appears anywhere in physics, in cosmology, in any application of mathematics to the real world, and they keep climbing. If you saw only the beginning of 1, 4, 26, 41, 60 rising relentlessly, you would bet everything you owned that it runs away to infinity and never returns. You would be wrong. In 1944, Reuben Goodstein proved that every single one of these sequences ends at 0. No matter the starting number, 4, 19, a trillion, the Goodstein sequence for it reaches 0 in a finite number of steps. The explosion always, eventually, reverses. The trickle always wins. How could anyone prove such a thing when the numbers grow beyond all comprehension? The proof is one of the most beautiful ideas in mathematics, and it works by leaving the whole numbers behind entirely. Goodstein's trick: take any term in the sequence, written in its hereditary base, and replace the base with the symbol for the first infinity, the smallest infinite ordinal, written as the Greek letter omega. A term like 2 to the base plus 1 becomes 2 to the power omega plus 1. You are no longer looking at a whole number. You are looking at an infinite ordinal, a point in the vast ordered landscape of infinities that mathematicians built to count beyond the finite. Here is the magic. When you bump the base and subtract 1 in the real sequence, the matching ordinal always gets strictly smaller. Always. The base bumping does nothing to the ordinal because infinity bumped upward is still that same infinity, but the subtraction pulls it down, and ordinals, no matter how large, have one iron property: you cannot decrease them forever. Any strictly descending sequence of ordinals must reach the bottom in finitely many steps. There is no infinite descent, so the ordinal sequence must hit 0, and when it does, the Goodstein sequence has hit 0 too. The explosion in the whole numbers is an illusion. Seen from the world of ordinals, the sequence was marching downhill the entire time. And here the story turns, because that proof required something arithmetic is not allowed to assume. Look again at what Goodstein's proof needed. It needed the entire landscape of ordinals up to a specific height, an ordinal called epsilon naught, the infinite tower, omega to the omega to the omega forever. And it needed to know that this landscape is well ordered, that you truly cannot fall through it forever. In 1982, Laurie, Kirby and Gerhard asked a sharp question: can you prove Goodstein's theorem using only the standard axioms of arithmetic, Peano Arithmetic, the foundation underneath all of elementary number theory? Their answer was no, not no one has managed it yet. No, as in, it is impossible. Peano Arithmetic is not strong enough to prove that epsilon naught is well ordered. That single fact lives just beyond its reach. As Gerhard Gentzen had shown back in 1936, it is precisely the strength that arithmetic lacks. And without it, the descent argument collapses, with no other route available. Goodstein's theorem is true, but it is independent of Peano Arithmetic. The axioms of ordinary arithmetic can state it, can verify it for any particular number you choose, and can never prove it in general. This is not a vague philosophical worry. It is Gödel's incompleteness theorem made concrete. Gödel in 1931 showed that every sufficiently powerful system of arithmetic contains true statements it cannot prove, but his example was a strange self-referential sentence engineered to say, "I am not provable." Mathematicians could reassure themselves it was a curiosity, a logician's trick. Goodstein's theorem is not a trick, it is a plain statement about adding and subtracting whole numbers, and it sits permanently in the gap Gödel discovered. So we are left with two kinds of unknowing, and they are not the same. With the Collat's conjecture, the question was whether the sequence always reaches 1. We do not know if it is true. We have checked hundreds of quintillions of numbers, and we believe it, but belief is not proof, and we raise the possibility that it might be unprovable, the way Gödel warned some truths are. Goodstein sequences show us exactly what that possibility looks like when it comes true. Here we are not in doubt about the answer. We know with complete certainty that every Goodstein sequence reaches 0, and we have also proven that the standard tools of arithmetic can never establish it. The knowledge is real, but it had to come from outside, from the infinite, from the ordinals, from a place Peano Arithmetic cannot follow. That is the deeper lesson hiding inside a sequence of climbing numbers. The axioms we use to reason about the whole numbers are not the whole truth about the whole numbers. There are facts, simple, concrete, true facts about addition and subtraction that those axioms will never reach. Not because the facts are complicated, but because truth in mathematics is larger than any single system built to capture it. A sequence starts at 4. It climbs past everything. It falls to 0. It always falls to 0. And the proof that it must lives in a country your arithmetic can see, can name, and can point to, but can never enter.